Everything you can see is almost nothing. Every star, every galaxy, every nebula, every black hole, every atom and every planet, every ocean, every living thing that has ever existed. All of it. Every particle physics has ever detected, every object astronomy has ever catalogued, everything, adds up to approximately 5% of the universe. The other 95% is something else, something that doesn't emit light, doesn't absorb light, doesn't interact with anything we can directly measure. We've never touched it, never photographed it, never detected a single particle of it in a laboratory, despite decades of trying with the most sensitive instruments ever built. And yet we know it's there, with extraordinary precision, because of what it does to the 5% we can see. This is not speculation. This is not science fiction. This is one of the most well-evidenced and least understood facts in all of science. And following it carefully, all the way to where our knowledge runs out, reveals something genuinely unsettling about the universe we thought we understood. The first crack appeared in the 1970s. An astronomer named Vera Rubin was measuring the rotation speeds of stars in spiral galaxies. The physics was straightforward, or so everyone thought. Stars orbit the galactic center the same way planets orbit the sun. The further from the center, the weaker the gravitational pull, and so the slower the orbit. Mercury moves faster than Neptune. Inner stars move faster than outer stars. Kepler's laws. Basic orbital mechanics. Nobody expected a surprise. The surprise was total. Stars at the outer edges of galaxies, far from the dense central mass, far from where most of the visible matter is, orbit at roughly the same speed as stars near the center. The rotation curve, instead of declining with distance, was flat. Stars that should be crawling were moving fast. Stars that should have been flung into intergalactic space by the galaxy's rotation were staying put. There was only one explanation consistent with the physics. There has to be more mass. Invisible mass. Distributed not just to the center, but throughout an enormous halo surrounding the visible galaxy, providing gravitational pull at the outer edges that the visible matter alone cannot supply. Without that invisible mass, the outer stars would fly off. The galaxies as we see them shouldn't hold together. They shouldn't exist. Rubin's finding wasn't immediately accepted. It was too strange. But it held up. Across hundreds of galaxies, in every spiral system measured, the same pattern. Flat rotation curves. Extra mass required. Invisible mass everywhere. That was clue one. Then came the light. Einstein's general relativity tells us that mass curves spacetime, and light follows those curves. Massive objects bend the paths of light rays passing near them, acting as gravitational lenses, distorting and magnifying the images of objects behind them. We observe this, beautiful arcs and rings and multiple images of distant galaxies, bent around massive clusters in the foreground. And when you use that lensing to calculate the mass causing it, and compare that to the mass you can account for from all the visible matter in those clusters, the numbers don't match. The lensing is far stronger than the visible mass can produce, by a factor of roughly 5 to 6. There is 5 to 6 times more mass in those clusters than everything we can see put together. That extra mass is invisible, but it's bending space-time. It has gravity. It's real. It's just not anything we can detect directly. Two completely independent lines of evidence, galaxy rotation and gravitational lensing, pointing to the same conclusion. Something massive, invisible, and ubiquitous. And then the simulations. The universe has structure. Galaxies don't scatter randomly through space. They group into clusters, clusters into superclusters, superclusters into vast filaments and sheets separated by enormous voids, hundreds of millions of light years across. This structure grew from tiny density fluctuations in the early universe, amplified over billions of years by gravity. When cosmologists simulate this, starting from the known early universe and running gravity forward in time, using only ordinary visible matter, the structure that emerges is wrong. The galaxies don't clump right. The filaments are too weak. The voids are too small. The simulated universe doesn't look like the real one. Add dark matter, in the right quantities, with the right distribution, and the simulated universe matches observations with remarkable precision. The structure we see across the entire observable universe, the largest structures that exist, requires dark matter to form. Dark matter isn't just explaining a local anomaly in galaxy rotation. It's the scaffolding, the invisible framework on which all visible structure was assembled over 13 billion years. Now, what is it? Let me start with what it's not, because this is where a lot of confusion lives. Dark matter is not antimatter. Antimatter interacts electromagnetically. It would annihilate with matter in ways we could detect, producing gamma rays we'd see. We don't see that. It's not dark energy. Dark energy is a separate mystery, the thing causing the expansion of the universe to accelerate. Different phenomenon, different evidence, different puzzle. The name similarity is unfortunate, but they are not the same thing. It's not black holes, at least not primarily. Compact, massive objects contribute some mass, but the distribution and quantity don't match. We can constrain how many black holes exist in various mass ranges, and they fall short. And critically, it's not ordinary matter in some form we haven't found: protons, neutrons, atoms. The physics of the first few minutes after the Big Bang nucleosynthesis, the process that created the first hydrogen and helium, tells us precisely how much ordinary baryonic matter the universe contains. It's determined by the relative abundances of hydrogen, helium, and lithium we observe today. The answer? About 5% of the universe, which is exactly the ordinary matter we account for. Dark matter is not ordinary matter hiding somewhere. It's not made of protons and neutrons at all. It's something outside the standard model of particle physics, something we have no confirmed theory for. The leading candidate, the one that's dominated the field for decades, is something called a WIMP, weakly interacting massive particle. A WIMP would have significant mass, possibly 10 to 1,000 times the mass of a proton. It would interact through gravity and through the weak nuclear force. That's it. No electromagnetic interaction, no strong force. It would pass through ordinary matter almost completely unimpeded. Billions of WIMPs, if they exist, are passing through your body right now, through the Earth, through the Sun, almost without effect. WIMPs are theoretically compelling because they arise naturally from supersymmetry, an extension of the standard model that many physicists find mathematically motivated. And they would have been produced in exactly the right quantities in the early universe to account for the dark matter density we infer. The problem is that we've been looking for WIMPs for 30 years with increasingly sensitive detectors and found nothing. Underground laboratories, shielded from cosmic ray backgrounds by kilometers of rock. Detectors cooled to fractions of a degree above absolute zero. Tank-sized vats of liquid xenon waiting for a single WIMP to scatter off a nucleus. The Large Hadron Collider searching for WIMPs produced in collisions. Space telescopes looking for gamma rays from WIMP annihilation in the galactic center. All of it. Nothing. Not a single confirmed detection. The most sensitive dark matter detectors ever built have returned silence. WIMPs remain the leading theoretical candidate and the leading experimental frustration simultaneously. So what else might it be? Axions, particles originally proposed to solve a completely different problem in particle physics, have gained significant attention. Much lighter than WIMPs, much harder to detect, but theoretically motivated and experimentally searched for. No confirmation yet. Sterile neutrinos, hypothetical heavier cousins of the known neutrinos, which interact only through gravity, are another serious candidate. Primordial black holes formed in the extreme density of the early universe before any stars existed could contribute some fraction of dark matter. There are experiments dedicated to each of these possibilities. The candidate space is wide open, and that's itself important information. Some physicists have taken a different approach entirely. Maybe the problem isn't missing matter, maybe it's wrong gravity. Modified Newtonian Dynamics, MOND, proposes that gravity behaves differently in very weak gravitational fields than our equations predict. In the weak gravity at the outskirts of galaxies, gravity would be stronger than Newton or Einstein say. And that extra strength would explain the flat rotation curves without any invisible matter. MOND works. For individual galaxies, it predicts rotation curves from visible matter alone with surprising accuracy. That's not nothing, that's actually remarkable. But it fails for galaxy clusters. It fails for the large-scale structure of the universe. And it has no good explanation for what happened in the bullet cluster. The bullet cluster is two galaxy clusters that collided approximately 150 million years ago. When they passed through each other, the ordinary matter, vast clouds of hot gas, slowed down. Electromagnetic interactions between gas clouds created drag. The gas piled up in the center of the collision. But dark matter doesn't interact electromagnetically. It has no drag. It passed straight through. Gravitational lensing maps show the mass clearly. Two clumps of mass, one on each side of the collision, separated from the visible gas in the middle. The mass is where the visible matter isn't. The mass passed through the collision while the ordinary matter stopped. That mass is dark matter, separate from ordinary matter, in specific locations, following its own dynamics. It's not a modification of gravity, because gravity is the same for both the dark matter and the ordinary matter. The dark matter didn't stop. The gas did. Something is there. The bullet cluster is the most direct visual evidence that dark matter is a real substance, not a modification of our equations. And yet, we still don't know what it is. Here's the honest accounting. We know dark matter exists. We know approximately how much of it there is, about 27% of the total energy content of the universe, compared to 5% ordinary matter and 68% dark energy. We know how it's distributed, in halos around galaxies, in filaments between galaxy clusters. We know it has gravity. We know it doesn't interact with light. We know it's not any particle in the Standard Model. And we have no confirmed idea what it actually is. The Standard Model of particle physics, the theory that describes every known particle and force with extraordinary precision, the most tested theory in the history of science, has no place for dark matter. No candidate particle, no mechanism. Dark matter sits completely outside it. Everything physics has successfully described, every particle accelerator result, every quantum electrodynamics calculation, every nuclear physics measurement, every atom in every star, is 5% of the universe. The rest is dark matter and dark energy, about which we have profound evidence and profound ignorance at the same time. We've been studying the universe for centuries, building better telescopes, better detectors, better theories. The Standard Model is extraordinary. It predicted particles before they were found, calculated quantities to 12 decimal places, passed every experimental test. and it describes 5% of what exists. The universe we thought we understood, the universe of particles and light and matter and forces, turns out to be a thin, visible layer on top of something vast and invisible that we've barely begun to understand. Every galaxy you've ever seen in a photograph, every nebula, every star cluster, every cosmic image that has ever made you feel the scale of the universe, is embedded in a dark matter halo 5 to 10 times more massive than the visible structure. The beautiful visible universe is the minority, the fringe, the small bright part of something much larger and much darker. We've been reading the universe by starlight, and it turns out most of the universe doesn't make any.